With this formula, we can now understand how the shape of the boat affects its rotational motion. If we compare this formula with this formula, we can see that this is the constant k. Now we know that if the boat has a positive k, it will have a stable equilibrium. Since W is always a positive constant, the boat will have a stable equilibrium if this quantity is positive. So if b cubed over 12a minus d is greater than 0. When this quantity is greater than 0, this means that the center of buoyancy always lies to the right of the center of gravity in this picture. And so it generates a torque in the opposite direction to the rotation angle, always trying to rotate the boat back towards its equilibrium position. The more positive this quantity is, the larger this lever arm will be, meaning you'll get a larger torque and the boat will be more stable. For example, from this formula, we can see that short and wide boats will be very stable. This is because a wide boat has a large B and a short boat has a small d. And so this quantity is large, meaning that the lever is large, meaning that the boat generates a large torque and it is stable. On the other hand, when do we get an unstable equilibrium? Well, we get an unstable equilibrium when k is negative. K will be negative when this quantity is negative, since again, W is always a positive constant. So we have an unstable equilibrium when b cubed over 12a minus d is less than 0. When this quantity is less than 0, in this picture, it means that the center of buoyancy is actually located to the left of the center of gravity. In this case, the two forces still generate a torque. However, they now generate a torque in the opposite direction, trying to rotate the boat further and further away from its equilibrium position. For example, we can see that tall and skinny boats are likely to be unstable. This is because a tall boat will have a large d and a skinny boat will have a small b. And so this quantity is likely to be negative, meaning the boat will be unstable. We have now developed a model in the form of a second-order differential equation that predicts the rotational motion of the boat around its equilibrium. Based on the shape of the boat, we can predict whether the boat will have a stable or unstable equilibrium. If the boat has a stable equilibrium, we can use this differential equation to predict the period of the boat's oscillations around this equilibrium. If the boat has an unstable equilibrium, we can also use this differential equation to predict how fast the boat will tip away from its equilibrium.